Hi, my name is Carolin Stellmacher and I'm a researcher in Germany at the University of Bremen. I will share our work today in which we explored the use of mobile devices as a substitute for specialized controllers in mixed reality. For the results, I will present our design space comprising user-derived gestures and user preferences for haptic feedback. Our paper carries the title Exploring Mobile Devices as Haptic Interfaces for Mixed Reality. And this is joint work with my colleagues at the University of St. Gallen, LMU Munich, and Chalmers University. Systems for immersive mixed reality traditionally consist of multiple hardware components, a head-mounted display and specialized interaction devices such as controllers or gloves. An important benefit of these devices is the large design space for simulating the tactile sensation of the virtual environment through various haptic feedback mechanisms. However, with the growing presence of mixed reality technology in workspaces outside the traditional office or in the future in entertainment and self-driving cars, there's a shift towards more mobile settings for mixed reality. Carrying the separate controllers to these changing locations alongside the head-mounted display will then become cumbersome and unpractical. While the integrated hand tracking feature of head-mounted displays removes the additional hardware, the absence of a tangible input device then limits strongly the rendering of haptic sensations. Haptics are, however, fundamental to the experience, especially when creating a synthetic reality. Therefore, there's a need for an interaction technique that, on the one hand, reduces the hardware burden of carrying specialized devices and that increases mobility, but on the other hand, also maintains the ability to render haptic feedback. A possible solution could be to substitute the specialized interaction devices with more ubiquitous technology that users carry with them anyway. For this, previous works have explored approaches using smartwatches, everyday objects, or mobile devices. Mobile devices in particular are widespread, and with their advanced sensing capabilities, they hold the potential of enabling object interactions in mixed reality. In order to turn a mobile device into a controller, two fundamental aspects have to be considered. User input, for example in the form of gestures, and user output, here haptic feedback. Past research concerning user input has often employed surface gestures and motion gestures, or a combination of both. This facilitates, for example, the movement of two virtual hands through space or the manipulation of objects, such as cutting through a virtual cube. However, these gestures are mainly limited to manipulating virtual objects. They do not allow a haptic exploration of object features, for example, stroking the round and smooth shape of an apple. This opens up the question of what gestures a mobile device controller need to facilitate for haptic object exploration. Previous works in the advancement of haptic output of mobile devices has, for example, proposed an actuated pin array on the device's edge or a shape-changing display. As these mechanisms were designed to haptically augment screen content, the question here remains of what type of haptic feedback is meaningful to simulate virtual objects and their tactile features. To answer both questions, we employed an exploratory research approach. The main study of this paper was an elicitation study in mixed reality, but before that we needed to identify virtual objects that cover a range of haptic properties for our second study. For that, we did an online survey with 50 participants who rated the tactile sensation of 100 objects based on size, shape complexity, texture, hardness, temperature, and weight as defined by Lederman and Klatsky. Based on the results, we identified 12 objects that cover the minimum and maximum variance of the 6 haptic attributes. The set contains a small paper clip and a large umbrella for size, a simple toothpick and a more complex shaped baseball glove for shape complexity, a smooth rice corn and the rough texture of a sandpaper for texture, a soft toilet paper and a solid clamp for hardness, a cold key and a hot flame of a candle for temperature, and a balloon and a hammer for weight. These 12 objects were then presented to participants in our second study. The second study was conducted in a within-subject design with 17 participants. Participants were the MetaQuest Pro headset and observed virtual objects that were placed in front of them within the augmented reality pass-through. The study task was twofold to support participants in the design process. In the first step, we asked participants to visually describe a specific haptic attribute, for example, the shape of a toothpick. We then asked them to demonstrate with their hands how they would explore the attribute. In the second step, we asked participants again to touch and explore the same haptic attribute. However, this time they had to use a mobile phone as an interaction device and incorporate this into the gesture. To open up participants' imagination, we characterized the device as a super-sensing artifact that has limitless capabilities in sensing and rendering haptic feedback. As part of the exploration, we also asked participants to imagine their ideal haptic sensation that should be expressed in real time by the device. The 12 objects were presented in counterbalance order. Our measurements consisted of the recordings of hand movements and verbally expressed thoughts. At the end of the experiment, we conducted a semi-structured interview. We analyzed all recordings with 4 researchers in an iterative process of open coding and thematic analysis. We identified over 200 individual gestures from which we derived 10 high-level gestures. We then mapped in a table the employed gestures to the haptic attributes and their respective minimum and maximum variance, which are visualized here by a plus and minus sign. The top 3 popular gestures were stroke, grip and move, and pinch. Stroke was the most versatile as it was employed for all 6 haptic attributes. For example, a participant stroked the back of the device to feel the long and simple shape of the toothpick that was mapped onto the 2D surface. Grip and move was, for example, used to test and feel the weight of the heavy hammer. Pinch was, for example, used in the case of the soft toilet paper to pinch the device as a placeholder for the paper. The attribute that was linked to the most gestures was temperature with 7 out of 10 gestures. 2 of them were exclusively for temperature, tap and hover. Participants, for example, tapped the flashlight of the device as a heat source. Some also hovered the hand above the device, expecting it to radiate heat from the top. A key aspect in the design across all gestures was the positioning of the mobile device relative to the virtual object in the user's hand. Based on this observation, we identified 3 distinct modes that the device can adopt during the interaction. First, object mode, then hand mode, and third, tool mode. In the object mode, the device acts as a physical representation of the virtual object. Touching the device was here interpreted as touching the object. In the hand mode, the device assumes a physical representation of the user's hand. As participants stabilized the device in their open palm, haptic feedback would mostly be perceived only at this location. In the tool mode, the device was used as a tool for indirect interaction with the object. Participants envisioned 11 distinct types of haptic feedback that can be broadly categorized into active feedback mechanisms, passive haptics, utilizing device features, or techniques that rely on proprioceptive sensation. Here we map the haptic feedback with the gesture types and the haptic attributes. The three most suggested feedback types were force feedback for 5 attributes, and then passive haptics and surface deformation with 4 attributes. Overall, combinations between gestures and haptic sensation differed a lot. While, for example, grip and move was combined with 8 distinct sensations, press was combined with only 3. A particular interesting finding is the rather low occurrence of vibration, which was mentioned for only 2 gestures to explore 2 attributes, as nowadays vibration is by far the most commonly utilized haptic feedback in interaction devices. We synthesized our findings into a design space that we visualized in the paper in multiple tables and illustrations. They capture the links between the performed user-defined gestures and the suggested real-time haptic feedback. As I showcased only the most relevant findings in this presentation, I would kindly refer to our paper for a comprehensive view of the results. In conclusion, our design space combines haptic attributes of virtual objects with user-defined gestures and with desired real-time haptic feedback. Our results also revealed 3 core modes as a mobile device. 3 core modes a mobile device takes on during the haptic object exploration. In the future, further research is needed to understand the impact of foldable mobile devices that have been recently reintroduced on the consumer market. Their foldable mechanism enables new types of device interactions that will likely extend our design space. While we singled out haptic attributes individually in this study, the demonstrated haptic explorations could be combined into a multi-haptic sensation. Future work should explore the design of mobile devices as a multi-haptic interface to allow a more comprehensive haptic experience. And this was the research work for our paper exploring mobile devices as haptic interfaces for mixed reality. We hope that our design space inspires and guides researchers and practitioners when designing future haptic experiences for mobile mixed reality.